Hello everyone, and welcome to the webinar, CARMA Simulation Update. My name is Zach Pleasant, and I'll be helping with facilitating today's webinar. This webinar is sponsored by the Federal Highway Administration and hosted by the National Operations Center of Excellence, also known as NOCO. As a quick reminder, if you don't know already, at NOCO, we offer a variety of resources to support the transportation systems, management, and operations community. On the upper right-hand side of your screen, you can see a box called Useful Links. You can browse through those links for TSMO resources and news. Previous webinar recordings related to this topic can be accessed from there. Now I'll cover a few logistics for today's webinar. We are recording this webinar, and the recording, along with the presentation slides, will be available through the on-demand learning section of our website. All the attendees' phones are on listen-only mode by default, but we'd like you to stay engaged by using the question discussion pod for comments and questions. We have a question and answer session at the end of the webinar, so if you have any questions, we encourage all of you to enter them in the questions pod as they come to your mind at any time. Questions will be read out loud one at a time by the moderator, and our presenters will answer each question. So that is all I have, and with that, I'll hand it over to our moderator, Nicole Pallado, to start us off.
Good afternoon, everyone. My name is Nicole Pallado, and I'm a communications specialist with Leidos, and I will be your moderator today. Thank you all for being here. We are happy to share this information with you today and also get your thoughts on the topic. Our presenters for today are Jim Ostrich, who is a Traffic Incident Management Program Manager with the Federal Highway Administration's Office of Transportation Operations at USDOT in Washington, D.C. We also have Pavle Bujanovic, who is a Technical Manager of the CARMA program's Reliability Research Track, where he focuses on CDA research related to traffic incident management. We also have Sajith Racha, who is the ITS Manager overseeing research projects, including the CARMA TSMO project, at the FHWA Saxton Transportation Operations Laboratory. Next, there's Larry Head, who is a Professor of Systems and Industrial Engineering and Director of the Engineering Design Program at the University of Arizona. And finally, we have Amir Giazi, who is a Principal Investigator for 2 CAV research projects working to enable CDA and enhance infrastructure efficiency. And with that, I will hand it over to Sajith so we can get started.
Thank you, Nicole. Hello, everyone. Thank you for joining today's webinar. I am Sajith Racha, and I'm the project manager for one of the projects from Federal Highways Research Program, CARMA, that is Cooperative Automotive Research for Mobility Applications. I'm sure that many of you are aware of this research program. So one of the projects under this program deals with transportation system management and operations, which is TSMO use cases, and using CARMA. The primary goal of this project is to advance CARMA ecosystem by enabling cooperative driving automation features for the vehicles to interact with infrastructure, like traffic signals, especially at the arterial level. Also, applying the CDA to enhance transportation system management operations and improve safety and efficiency. So the main objective for this project is to develop concept of operations and proof of concept testing for several TSMO use cases that were identified by the project team. One such use case that we are working currently is the traffic incident management, and we would like to discuss today on that particular use case. Today you'll be learning about how CARMA ecosystem would contribute to the development of TIM use cases, which is traffic incident management, use case scenarios in cooperative driving automation environment, and how the CARMA ecosystem could better serve the traffic incident management community goals and expectations, and the functional needs and requirements for developing and deploying the incident management applications in CDA environments. So along with me, we have Amir Giazi with us today, who is one of the principal investigators on this project. We also have Larry Head from University of Arizona, who is helping us with our research on this project. Amir and Larry will be talking more on the framework shortly. We also have Govind Vadakpat, who is the Government Task Manager for this project from Federal Highway. And we have Pavle Bojanovic from Federal Highway, who is leading this particular use case effort. And he will be providing an overview of CDA program very shortly. Lastly, we have Jim Ostrich from Federal Highway, who is representing the traffic incident management community with us. I would like now Jim to provide his remarks to the incident and emergency management stakeholders. Jim?
Thanks, Sujit, and I'd like to thank everyone for joining us today. Big welcome. This is super exciting for me and hopefully for you. I see, I peruse real quick through the attendees list and I see some familiar names and some that I'm not familiar with, but it just shows your interest and commitment to the technology that we have here before us. As Sujit said, today in particular, well, first I want to say real quick, the community, the responder community, when it comes to traffic incident management activities, response, whether you're in an urban signalized environment, interstate, and for that matter, rural, remote roadways, the discussion today regarding transportation TSMO, as Sujit said, Transportation System Management Operations as it relates to TIM, is really gaining momentum. In the community, whether police, fire, rescue, EMS, towers, transportation, public works, they all have expressed the desire and a commitment to supporting in any way they can. And you're going to hear and see here very shortly the activities and the work that our team is doing. And so again, I want to thank you all for being here and being a part of it. I would also add that specifically, whether it's, cooperative driving automation, specifically to traffic signal preemption, or just CARMA messenger or CARMA tests that we're going to be doing in the field, even though we're still in a pause position, if you will, because of the pandemic, as far as being out in the field in person. I'm super excited that that's going to come here eventually in the near future, and hope that you continue to be part of our national team. So with that, I'll turn it back over to Sujit.
Thank you, Jim.
Thank you.
Okay, before we jump on to today's presentation, I'd like to read the disclaimer that this presentation was created and is being co-presented by both Federal Highway Administration and the contractor. The views and opinions expressed in this presentation are the presenters and not necessarily reflect those of the Federal Highway Administration or the US DOT. The contents do not necessarily reflect the official policy of the US DOT. So today, we will be providing you with quite a few topics, and here is a quick agenda of today's items that we are going to be discussing. We'll start off our presentation talking about some TSMO, which is Transportation System Management and Operation for Traffic Incident Management. And then we'll be giving you an overview of what CDA, which is Cooperative Driving Automation, means, and what is the CARMA program, and and the relation between CDA and CARMA, and provide those overviews on that. And we will also be talking about, especially for this particular use case, a system that is related to handle the operations, which is multimodal in intelligent transportation system, which is MITS. And Larry will be providing overview on this concept here. And we will then be talking about connecting TSMO and TIM using the CARMA ecosystem. And there were several scenarios, like I mentioned earlier, that were identified by the project team that can be benefited by applying, CARMA and with the CDA concept in there. And we would like to know from you, finally, if there are any additional information that you guys would like us to share, and we can quickly wrap up with some questions and answers that you may have. With that, I will pass it on to Nicole to get some initial information from the audience, and then we can get started with the presentation.
Thanks, Ajit. We'd like to take a brief pause here to ask everyone what brings you here today. So feel free to respond in the chat pod with your organization and your role so that everyone can get a sense of today's group. So let's just take a pause here and respond in the chat pod. Great, lots of responses. Thank you, everyone. Feel free to keep populating the chat pod, but I think we can start digging into it. So I will hand it over to Pablo.
Thank you, Nicole. Thank you, Sujit. Hi, everyone. My name is Pablo Bujanovic, as Nicole had mentioned earlier, and I am a technical manager here within the CARMA program, specifically focusing on our reliability use cases. So that includes things such as traffic incident management, weather, work zone, things like that. As part of this project, our CARMA TSMO project, we have a few different things that we're working on. And so the purpose, the objective of this project, where it comes to TIM, in addition to creating the ConOps that the team will be discussing later on in the presentation, is to be able to see how we can leverage CDA, Cooperative Driving Automation, to help us with traffic incident management, and specifically with traffic signal preemption. And so in order to do that, what we're going to do is we're going to use the various systems that are offered as part of the entire CARMA ecosystem, including the cloud, CARMA Streets, CARMA Platform, and others, in order to first show the technologies that we're developing in simulation, and then also in a field test environment. So you may be thinking to yourself, or some of you may be thinking to yourself, that traffic signal preemption already exists, and why are we continuing to do something? Why aren't we building a new technology? And the reason behind that is we want to see how can we use cooperative driving automation to make it better. So for example, what about in the future, perhaps we could have a first responder communicate with CARMA Cloud and say, hey, we're going from A to B, and now CARMA Cloud can already communicate with all the traffic signals along that route to get them prepared for the first responder to come through those intersections right at the right time and have the minimal impact on traffic. We can also look at what about doing traffic signal preemption across multiple jurisdictions, or where the different standards are being used and with traffic signals, things like that. So these are the types of questions that we want to be able to answer as part of this project. And we acknowledge when we have to employ traffic signal preemption, and as well as any sort of incident response, these are not normal operations. These are exceptions to the normal operations. And so during these moments, safety of the first responders and safety of the rest of the transportation community is of utmost priority. And then after we've taken care of the safety, we want to look at how we can also work to improve the mobility of the incident response vehicles and also of other vehicles in the vicinity. So with that, before we get into it, let's just quickly have a brief overview of what CDA is. I'm sure that many of you are familiar. Just for some of you who may not know exactly what it is, so basically CDA is the idea that we can use machine-to-machine communication to leverage the idea of sending and receiving messages back and forth to allow the transportation network to receive the maximum possible benefits. So the way I kind of see it is, as opposed to 5 independent basketball players on a team that haven't really practiced together, I think about CDA being how do we work as a finely tuned machine where everybody gets the maximum benefit for the entire system to make sure that we're all staying safe when we're progressing through traffic as smoothly as possible. So down here at the bottom, you can see a link. The SAE J3216 standard that was actually passed last May, so about a year ago, that actually explains in technical terms exactly what CDA is. And if you are interested in this, I encourage you to go ahead and download it. It's one of the few SAE standards that are actually currently available for free. Most of the time their standards are not, but this one is. So please go ahead and download it if that is of interest to you. So getting a little more specific into the SAE J3216 standard, as you guys can see across the top row, we have the SAE levels of automation 0 through 5 that I assume most of us are familiar with level 0 being absolutely no driving automation to level 1 being the lane keeping and the adaptive cruise control that some of the vehicles today have, all the way to level 5 where you have full driving automation, so that's where you wouldn't even have a steering wheel. But then as you can see over on your left, there's also a column that has the classes of cooperation that have been introduced with this new standard. So there's 4 classes of cooperation, as you see, Class A, B, C, and D, and they kind of progress in terms of what sorts of cooperation is happening between vehicles depending on which one of these classes is being employed. So with Class A, we have status sharing. So this is your basic safety message, the here I am part. So, we'll send our position, our acceleration, our velocity, but also what I see. So this is, we might send our sensor data. And so this will actually allow us to be able to engage in something like cooperative perception in order to help all vehicles around us have a better awareness of their surroundings. After that, we have Class B, which is intent sharing. So that includes all that stuff that you saw in Class A, but also what if now we send information on what we're going to do in the future. So maybe trajectories of the next 5, 10, 15, 20, 30, or 60 seconds of here's where we plan to be going. And so other vehicles can use that information and can kind of do some kind of conflict management. Hey, are we going to stay safe if you continue to use your trajectory and I continue to use mine? After that is Class C, which is agreement seeking. So this is where we actually take the intents, but now we actually try to negotiate with other vehicles to maybe make some space for us in order to make sure that we're staying safe. So for example, if I'm trying to merge into a congested highway, perhaps I might communicate with a vehicle around me and ask them to create some space for me so that I can merge in safely. And then lastly, Class D, that's the prescriptive piece. That's where we say, I will do as directed. So this cooperation class won't be used that often, but it certainly can be used in traffic incident management. So for example, if we have a first responder addressing a situation, he may tell you, hey, you need to pull over and make way for me. So that would be an example of prescriptive. Or for example, if we're platooning together and we voluntarily choose to join a platoon, then once you're in the platoon, you have to follow the rules of that platoon, right? So you can't go rogue and do your own thing. If the platoon has, for example, agreed to go at 70 miles an hour, you can't say, okay, I want to go at 75 miles an hour, as long as you remain a member of that platoon. Okay, so before we get into talking a little bit more about some of the use cases that we're working on and talking about the ConOps document that we've been working on as part of this project, I just want to encourage you guys to be on the lookout for these 2 documents that we will be publishing soon. The first one is the high-level concept of operations, examination of the relationships between TSMO strategies and CDA. And then the second one is the detailed ConOps, TSMO/CDA use cases and scenarios. So these two documents, what they do is they go in depth into these 4 use cases that are written here. So basic travel being when there's no specific event going on, but it's just, the regular congestion that we experience every day, and how do we try to increase mobility and safety during those moments. And then also we have our traffic incident management, road weather management, and work zone management scenarios that we're trying to improve through CDA. So with that, in order to be able to look into CDA questions and research problems, we have started the CARMA program, which I'm sure that many of you are familiar with. But for those of you that are not, just really briefly, what the CARMA program is that it's an initiative by Federal Highway to develop software systems, namely the platform, the cloud, messenger, and streets, which are basically open source systems that sit on different parts of the transportation network, whether that's on in the cloud, on the infrastructure, on the vehicle itself, and it's supposed to allow researchers to be able to install this on their own equipment and then do a research and then use it to answer CDA questions. So, for example, they might develop their own feature about platooning or speed harmonization or traffic incident management using these CARMA systems. And the reason that we've done this is because what we want to do, we realize that we don't have an unlimited budget here at Federal Highway. We know that other researchers and academics, they don't have this sort of ability of an unlimited budget either. And so what we want to do is we want to leverage each other's work. So by creating this CARMA program and creating a community of people that will be developing CDA features and then submitting it back to us, and then future researchers can use their improvements and develop even better CDA applications. So with that, I just want to quickly show two different applications that we're currently working on, that we will be working on. So the first one is the move over law. And so here, basically what we have is this white vehicle at the Chevy Tahoe. He represents a police vehicle, and he's pulled over this Infinity vehicle on the side of the road, and he's created a buffer. He has the police officer, and inside the vehicle has a as user interface, as a tablet, and he's able to create a geofence around him to vehicles to say, hey, you can't enter into this area in order to make sure that we're keeping our first responders safe. And then the vehicle around him now has to, as you kind of see, move over a little bit and also decrease his speed to make sure that we're keeping a safe transportation network during this event. So this is a use case that we will be demonstrating this summer, and so it's almost ready to go. And then another use case that we're currently looking into, and we hope to be able to deliver it with a future project, is something like this, as you see here, where we actually have traffic signal preemption across with multiple vehicles across multiple intersections, and then at the same time what we're doing is we're communicating. We're using Class D communication, as you see here, with other vehicles, and these vehicles are now starting to pull over along on the side of the road to make way for these fire trucks that are coming through to address an emergency. So as you see upstream, most of the vehicles are already pulled over and waiting for the fire trucks to get through, and then downstream these vehicles are beginning to pull over because it's just been communicated to them that they need to do that. So with that, what I'll do next is I'll hand it over to Larry so he can talk a little bit more about the different use cases that we're addressing as part of the TIM work that we're doing.
Thanks, Pablo. So I wanted to talk about the TSMO use cases really related to the traffic signals. And so the different use cases that we might consider is doing nothing, so not preempting the signals, and we sort of like that as the base case. And then what we're used to more today is basic single intersection preemption, and then possibly route level or multi-intersection level signal preemption, and then doing things like clearing the queues before the emergency vehicles arrive at the intersection, we can use preemption for that. And then if we wanted to be a little more creative, maybe we could do it on a single lane by lane basis so that we clear the queue in the lane that we need so we have the downstream capacity that's there. So I'll talk through these different use cases that we're looking at. So I think this is the traditional one that most of us are familiar with. We have a signal with some vehicles and an emergency vehicle approaching there from the left, and it communicates with the infrastructure. In our case, we envision the communication being using the Cooperative Driving Automation platform and get that traffic signal to turn green as soon as possible. The second case, is a similar case to the first one, but this time we might know that the response vehicle is going to go through multiple intersections. So if we know it's going through the first intersection here and then it will go through the second, whether it's turning left or going straight or whatever is along its route, we can begin to get that second signal green and get some of the vehicles cleared out before it gets there. The third use case is the queue clearance use case. And so if you can imagine at a downstream signal, if you have a large queue and there's some congestion down there, maybe we need to do something in advance to clear that queue out. And so in a cooperative driving automation environment, we have a lot of information about those vehicles that are there, and they're automated vehicles, we assume, and that we will be able to get that information and use it to determine how much earlier we need to start the green time to be able to clear the queue out. And then we could do queue clearance with single lanes. So in the situation that's shown here, we have both lanes are green for vehicles traveling down the roadway, but we might be able to just have one lane green to flush the queue out of that lane so there's a path for the response vehicle to go through and hold the other lanes red. And then that creates downstream capacity also, so there's a place for the vehicles that have to clear the queue to go. So these are, I think, pretty basic traffic signal preemption use cases, and we can envision that the CARMA platform and the CARMA ecosystem gives us the tools that we need to implement this at both the system level and the intersection level and with the vehicle as a cooperative member of this. So the CARMA program ecosystem is really a collection of products, as you've heard from Pavli: CARMA Cloud, CARMA Platform, CARMA Messenger, and CARMA Streets. And we'll talk about each of those. And they're really being used for evaluation, right? It's a platform for doing research and deployment by using simulation. We can do safety analysis and compute some safety measures and consider things like human factors and driver in the loop. We can do testing of these different kinds of concepts. It has a rich analytics framework to be able to collect data and do analysis. And there's also an effort going on of 1/10 scale vehicles to actually do some testing with some vehicles, not on full-size vehicles. One of the important things about the CARMA ecosystem is it's really creating a community for collaboration, and they have a great support system that's there. And I know that others are going to talk about that coming up. As Pavli mentioned, he's really involved with the reliability research track and the use cases associated to it, with like work zones, weather, and traffic incident management. We had an earlier webinar that was probably very similar to what we're talking about today on the traffic side, where we talked about transit and traffic signals and congestion. Okay, and so the difference is, as Pavli mentioned, with transit, it's a normal part of the traffic stream. With traffic incident management, it's an exception to being a normal part of the traffic stream. So the things we're doing are different, and while in both cases we're really worried about safety, in the reliability case, safety is a much higher concern because of the exception type behavior. And then there's another research track that's dealing with freight that has to do with commercial motor vehicles and port use cases such as port drayage, commercial vehicle operations, and truck platooning. So Nicole, I'm going to hand it back to you for the audience interaction.
Great, thanks, Larry. So we've gone through some use cases and scenarios so far, so we'll take another pause here for a moment to see if you are finding these helpful or beneficial in your work and experience. So if the answer is yes, please click the raise hand icon at the top of your screen. If you can't find it, you can just respond in the chat pod. That's fine as well. And if the answer is no, then we would also love to hear your thoughts. We love constructive feedback. So let's just take a moment for that. Great, thank you, everyone. I think we can keep moving on, but please feel free to keep populating the chat pod, and also add any questions you have that we can get to during the question and answer portion at the end of the presentation. So I will hand it back to Larry.
Larry, are you on mute?
Okay, I think my microphone is turned on now. Can you hear me, Pablo?
Yes, we can hear you.
Okay, great. So yeah, I just want to talk a little bit about CARMA Cloud. So CARMA Cloud is this system layer view of a transportation system. So in the system layer view, we have information about different things going on in the network, the traffic signals, the incident response vehicles, things from traffic management services such as weather, work zone, and incidents, maybe information from the transit management system about the route schedules and vehicle status, and then other kinds of data that may be made available to the public. And CARMA Cloud then communicates with CARMA Streets, which is a new CARMA component that Amir's going to talk about, which exists at the edge. And that gives some processing for cooperative driving automation data and decision making right at the edge, and it can communicate with ITS infrastructure devices such as traffic signals and other control devices that are out there. And then to go along with that, we have the Messenger. The CARMA Messenger is a system that's been developed to allow communication with non-automated driving system vehicles. And then CARMA Platform is really the platform that is there on the automated driving vehicle. And it's making decisions about the driving and operation of the vehicle, but also can be an active participant in the TSMO system in terms of vehicles sending requests for information and such. And so in CARMA Cloud, we can have different layers of information, like we might have model layers for events and traffic and control and infrastructure and geophysical and transit and maybe incident management. And then we might have system objects that go along with those. And these objects can be available across the different kind of applications that are there. So if we're doing traffic incident management, we might know about work zones or other traffic events. We might know from the traffic layer things about congestion. We might know weather information, right? And then in traffic control, where the signals are and what state the signals are in, or what other kind of signage and marking and things are available. We might know about the infrastructure, if there are roads and bridges. If with the weather information and bridges, we might want to adjust speeds of vehicles that are traveling. And so really the way that I think of CARMA Cloud is it's this rich information layer that is integrated together that allows us, when we're developing algorithms and doing research, whether we're at the edge or at the system level or on the vehicle, to get access to very important information. So I'm going to turn it over to Amir to talk about the new CARMA Streets platform.
Okay, thanks, Larry. Can you hear me?
Yes, I can hear you.
Yes,
Okay.
we can.
So good afternoon or morning, everyone, depending on where you are. So at this part of the webinar, I want to provide an overview of CARMA Street, which, as Larry mentioned, is one of the components of the CARMA ecosystem. This slide shows a high-level system framework of the CARMA ecosystem. So as Larry mentioned, CARMA Cloud deals with a kind of wide area coordination of traffic operations like, the work zone information, lane closure information, weather, etc. So CARMA Street is a local interface or an edge between the cloud and the roadside infrastructure that helps with collaboration between different elements of the system. So as you see in this figure, CARMA Streets provides an interface between different components of the system, like the cloud, the roadside controllers and sensors. Also, it can communicate with the surrounding vehicles through CARMA platform and CARMA messenger. So in addition to the interface functionality, CARMA Streets also serves as an edge computing device to basically process optimization problems and calculate different real-time model variables. So for example, in the team application, CARMA Streets can estimate the arrival time of the emergency vehicle to the intersection and calculate other relevant variables like the queue length, the signal timing adaptations, and all that. And then it can also transmit that kind of information to other connected units like the signal controller and the CDA vehicle. So this slide shows the basic CARMA Street system architecture. Basically, within the intersection communication radius, roadside units can also collect the vehicle's status and intent information and transmit that to CARMA Street. As mentioned, CARMA Street has some computational capabilities. So with that information, CARMA Street can calculate certain planning variables and send that to the roadside unit. Then the roadside units can broadcast, those variables along with the other vehicle's status and intent information. So what happens if we add a traffic signal controller to the architecture? So the system context mostly remains the same, but the CARMA Street can consume the signal phase and timing messages from the signal controller, and it can send that to the roadside unit to be broadcast to the surrounding vehicles. Also, in the team use case or applications, emergency vehicles can, send signal request messages to the signal controller through RSU and CARMA Street. So in addition to that, we have another interesting feature that CARMA Streets will be able to support, that is cooperative perception. So I don't want to go into details of this feature. In fact, we have another webinar for that in the next few weeks. But the idea is that, in the CDA environment, vehicles and infrastructure can share perception information with each other and, to basically increase their perception about the surrounding environment, which potentially can, significantly improve the intersection safety. So in this architecture, the presence of pedestrians, bicyclists, and other, vulnerable road users could be notified to the emergency vehicle so that they can, operate more safely. So we talked about CARMA platform in CARMA Street system architecture, but we did not explain that so much. In a nutshell, CARMA platform is an open source software that enables CDA features on a vehicle equipped with, required hardware. As you see in this figure, it has three main stacks, and each of these stacks contains several elements and modules. So basically, first it sends the environment using the sensors and devices and proper modules. As mentioned, it may also receive some information from other CDA entities like, CARMA Street. Then with that, it plans the vehicle maneuvers. As an example, in the team use case, a priority request generator module could be part of the plan stack to send requests to CARMA Street. And finally, it executes the plan in the act stack according to the outputs of the previous stack. Now, before handing the webinar presentation over back to Larry, I would like to quickly talk about some additional activities that are going on in the CARMA program. We are currently developing the CARMA Cloud and CARMA Street, so we will be providing some more information about those products in next few months. For CARMA Street, we are going to use and demonstrate its functionality on our TSMO use cases that are transit management and transit traffic incident management. In addition to that, we have another very interesting research called CARMA 110. So for that, we are implementing some of our CARMA platform capabilities on scaled-down test vehicles to basically test and showcase CARMA with much lower expenses, risk, and liabilities. We have another interesting project called CARMA Port Trace. In this project, we will demonstrate a proof of concept application to support the port management use case using the fleet of our 4 CARMA-equipped heavy vehicles. And last but not the least, we have a no-cost support from our CARMA support services that aims to basically address any questions or issues related to CARMA. So this slide shows 2 communication and support channels for CARMA research and development. CARMA Collaborative is the channel for industry-wide collaboration on CDA R&D through the CARMA program. Basically, it aims to engage diverse stakeholders, including academics, public agencies, private companies, and industry associations to accelerate CDA R&D. On that, we also try to advance CARMA, encourage peer exchange and demonstrate the benefits of, of that industry adoption. So if you're interested in joining our community of CARMA users and stakeholders, please email karma@dot.gov. We try to hold, regular webinars with CARMA updates, as well as maybe some channels, conference sessions, and technical working groups. As mentioned, CARMA Support Services is the main point of contact to answer your technical questions and issues related to CARMA research and development. So if you have any technical questions or support, please email to karmasupport@dot.gov, and our team, will provide you with the support you need. In addition to that, CARMA Support Services develop and deliver training, guidance, and materials, and also some documentation to assist CARMA users and collaborators. The documentation is available online on our CARMA Confluence pages, which is shown in the next slide. So to learn more about CARMA, I encourage you all to visit our these online resources shown here. And I think they are, they're also posted in the links part of the webinar window. Now with that, I will hand it back to Larry to continue on the team discussion.
Yeah, so I hope all of you feel like I do, that the CARMA platform and the CARMA ecosystem is actually a very exciting research enabler. A lot of the time that we've spent in the past years, or my group has spent in the past years, has been implementing services and things to be able to talk to traffic controllers and other, organizing data and things. And so these components really give us the platform. So if we think about what this could do for us, and we think about what could CARMA Cloud do, what role could it play in a traffic incident management system for TSMO? So it could provide information like the location of the incident, where the response vehicles are, the routes the vehicles are going to take when they're responding to the incident, the status of the network, like where are the work zones, where are there other incidents on the network, where's their traffic congestion, is there weather impacting the network, such as flooding or snow and ice and other things. We could think about the role that CARMA Streets can play. And CARMA Streets there at the edge, it can provide a lot of connected vehicle services. It can do things like the multimodal priority control, the work that we've been doing on the MIT system and providing the preemption. It can provide intelligent signal control. It can do things like estimate queue length and provide information that's going to be useful. And it can be a player in emergency vehicle alert. Now, I know the purists among us would say, well, in the J2735 standard, the emergency vehicle alert message is a vehicle-to-vehicle message. But I would contend that the edge needs to be, the CARMA streets needs to be involved, because when you're in an urban canyon and you've got response vehicles coming down one approach, getting the information out on the other approaches may require the infrastructure to relay that information. So I think it could be a player there. And then the CARMA platform, in any kind of cooperative driving automation that we do, the vehicle platform is a very important player in the system. So in a traffic incident management and doing preemption and priority, the vehicle is the one that should probably generate the request for priority. It knows where it's at, it knows its speed, it knows that in real time. It has an interface to the lights and sirens system. So through CARMA platform, we could know whether the lights and sirens are active, and it can also be the one that's generating that emergency vehicle alert message. So they map nicely to Class A and some Class A and D type behaviors. And when we do talk about Class D behavior here, we really do think of automated vehicles that are downstream from response vehicles that need to get out of the way. And so they can be told, vacate the lane and get out of the way. So it's one of the few real Class D use cases, I think, that makes sense. So I wanted to give a little background on the MITS project for people that aren't that familiar with the project. And the goal of MITS was its multimodal intelligent traffic signal system. And the goal, when we started this in 2014, it's a connected vehicle pool fund project. The goal was to develop a new generation of traffic control system that actually utilizes connected vehicle data that's communicated wirelessly to the roadside units and edge processing that can work with traffic signal controls to do things like provide intelligent signal control. So we often think of adaptive control, but in traditional adaptive systems, whatever we think of as traditional, but in adaptive systems, we don't actually know where all the vehicles are. But in a connected vehicle, in a cooperative driving automation, we would know where the vehicles are, and we can do intelligent signal control in much improved ways. We can provide priority and preemption for emergency vehicles. We can provide priority for transit vehicles and priority for freight vehicles. And we can do the priority framework for all of the vehicles are considered at the same time. Now, clearly, vehicles like emergency vehicles might override transit vehicles and freight vehicles, but there are use cases where a freight vehicle might be in a dilemma zone and an emergency vehicle has requested preemption where we would want to go ahead and clear the freight vehicle before moving on to the emergency vehicle. And then finally, the MITS pedestrian application to be able to involve the vulnerable road users in the traffic signal control system. So as I mentioned, this is a connected vehicle pool fund project. It's through the University of Virginia. The partners are the University of California, Berkeley, the PATH program, and the University of Arizona. The champions in the project have really been Maricopa County DOT and California DOT, along with Federal Highway Administration. And we've had great partners from Texas DOT, Virginia, Minnesota, Utah, Florida, and many other partners, Delaware and others that are out there. There's a couple of links in the presentation here so you could get some information about the MITS project. At the highest level, the MITS really has what we call policy-based control. We think of dividing the traffic system or the transportation system into different sections, and maybe the sections have different traffic control philosophies. Like in the example shown here, Section 1, this might be a section where we're moving a lot of freight vehicles in and out to the interstate. There might be factories and warehouses and things that are there, and through those signals, we would want to have freight priority to be a very high form of priority. But of course, the hierarchy over on the left shows that rail crossings, which of course have to be the highest level priority, and then emergency vehicles, and then freight, and then maybe coordination, transit, and pedestrians. And this other section of the network, maybe this is a section where there's lots of schools and shopping and pedestrians, and we really want to encourage the use of public transportation. and walking. And so maybe the priority in that network would be, of course, rail crossings and emergency vehicles, but then transit. And maybe within transit, it's let's use the BRT and the express, or maybe just late local vehicles, and then give some priority for pedestrians and then coordination and freight. So the goal of MITS in using this policy-based control was to be able to set a hierarchy based upon the operating principles in the corridor where you're operating. And then, of course, in any kind of cooperative driving automation or connected vehicle system, the fidelity of the data that we get allows us to observe performance. And so we can do it by mode, by movement, and by section. Things like volume delay, travel time, throughput, stops, new measures like smoothness of traffic flow and the amount of time a vehicle spends in the system can be used for assessing vehicle performance. And so MITS was really developed, with this idea of connected vehicles in mind, and so it uses the J2735 messages. It uses MAP, SPAT, basic safety message, signal request message, and signal status message. The signal request messages are for the emergency vehicles, transit, and trucks that are there so that they can request special consideration and service. When MITS receives these SRMs from these special vehicles, it maintains a list of all of the active requests, okay? And then it considers that list and the hierarchy that the operating agency has set up to try to best implement signal timing to accommodate them. So where in traditional preemption and priority systems, it's usually a first come, first serve, MITS can consider multiple requests for priority and preemption. If there's 3 or 4 emergency vehicles approaching a traffic signal and maybe a couple of transit and trucks, it can override the transit and trucks, but say for these 3 or 4 vehicles, what is going to be the best thing that I can do for the collection of vehicles? It uses the hierarchy that I've talked about. It has coordination that is yet another form of priority. We just think of coordination as being a form of priority. We want the signal green for a group of vehicles to progress down an arterial. That's the same as we want the signal green for a truck or a transit vehicle or an emergency vehicle to progress down through a group of signals, okay? It solves, every time we get this collection of requests, we solve what's called an optimal scheduling problem that considers things like the controller structure. Is it dual ring, 8-phase? What are the minimum green times, the walk times, the pedestrian clearance times, yellow and red? When we do things like preemption, we're very aggressive, and we may omit phases that would put vehicles on conflicting movements with the movement of the responding vehicle. This is probably a difficult slide to read, but the point of the slide is to take the MITS architecture, which on the left side consists of a vehicle side processor where the priority request generator resides and where it generates the SRM message that then is sent over the wireless communication from the OBU to the RSU to the MITS roadside processor, or think of that as being an edge processor where the priority request server resides. And that is where this collection of priority requests is managed, and then the scheduling problem is solved, and then it's implemented on the signal controller. And that's also where coordination is managed. And then finally, we have a management system at the higher level that allows you to do configuration and collect data and things. And so I really think that the CARMA cloud ecosystem is an ideal environment for us to implement MITS. The CARMA platform is exactly what we're doing with the vehicle side processor. The difference is it really can do more than what we do with the vehicle side processor and the priority request generator. It can provide opportunities for using emergency vehicle alert and other CDA type capabilities. CARMA Streets is that edge processor. So in the MITS project, we use a MITS roadside processor. We use an Econolite connected vehicle coprocessor board that's a field hardened board that can go out in the streets. But the CARMA Streets can run on different kinds of hardware and give us, again, another set of CARMA services. In MITS, we have to do message encoding and decoding and receiving and managing and collecting data and do all of that. And those are integral services into the CARMA platform and CARMA Streets. And then finally, CARMA Cloud will it allow us to get access to that data about the broader transportation network and use that information perhaps in making some of the decision making. And so our goal is to bring these pieces together The MITS components, the priority request generator that does the location of the vehicle on the map, estimating when it's going to arrive at the stop bar, determining its eligibility, like is the lights and siren interface on, right? If it's eligible, then it would send the SRM. CARMA platform can provide the encoders and decoders and the data capture that we're doing today. The CARMA Streets can provide the priority request server functionality without us having to worry about message encoding and decoding. So it can manage the multiple priority requests, it can implement the policy as set up by the operating agency, it can solve the scheduling problem, it's the algorithm that's part of MITS, it can populate the SPAT data with MITS schedule information. When the signal controller is running essentially in a free mode and we're doing the coordination and we're doing the priority, we need to replace the SPAT data with key MITS data. We can implement the optimal schedule on the traffic signal controller, and we do that using NTCIP. So I think that the CARMA Streets is a great place for us to do that. And then new capabilities, we would like to know where the incident is located. What routes are the vehicles going to take? Oftentimes in today, in the connected vehicle implementation, we don't know the route of the vehicle. So if it's approaching on one approach, we don't know if it wants to turn left or go through. So we have to make accommodations accordingly. It would be great to know. We would like to know where the work zones are, where congestion is, where incidents and weather are occurring. And then CARMA Cloud also with its rich platform of analytics to support simulating the estimation of the benefits. That can become a key part of maybe routing decisions and decisions about doing downstream control and such. Analytics for the performance data, and then it's always useful to have a platform that can help us manage the configuration and do supporting and troubleshooting and management. So we don't have to create all of that on our own. So what we want to do is we want to take the use cases that we presented, we want to take the CARMA ecosystem that we've discussed and the MITS capability that's been the research that we've been doing over the last several years, and we want to bring it together and do that by talking about some TSMO traffic incident management scenarios. And I really just identified 3 here that we want to use. So if we think about a basic arterial with an incident located somewhere and the response vehicle operations, we have Class A, we can inform non-automated vehicles that were there and hopefully they would move over, right? We can inform Class D vehicles that are automated that they need to move over, or they're commanded to move over. We can use some of the MITS preemption capability to provide traffic signal preemption in a very intelligent way for multiple vehicles by limiting the movement on conflicting movements where we don't need vehicles to be there, that I think will give us the benefit of reducing conflicts. And that's why we do the research. We want to be able to measure, have we reduced the conflicts, have we improved the travel time through the intersection. We can do a scenario with route priority, where we can reduce the signal delay by having multiple signals along the route, working to get ahead of the congestion and the queues and things that are there. It may have an impact of increasing the signal delay for the non-priority vehicles, but this is an exception event. This isn't, when we talk about transit signal priority, we worry a lot about the impact, but when we talk about traffic incident management, we worry much less about it. And then finally, if there's a work zone, and what could we do if we knew we were introducing emergency response vehicles into a work zone? So here's the basic scenario. We've got, a group of signals along an arterial or along a route. Doesn't necessarily have to be along the arterial. The vehicles could be turning left, and they are requesting and being granted priority. They're notifying the automated vehicles that they're there and they need to get out of the way. They're alerting the non-automated vehicles that they should get out of the way. And so by doing this, it should make for a much smoother flow of the incident response vehicle as it moves through the location. And so I showed up here an incident location on this right intersection upstream where these vehicles will want to progress through, clear the traffic that's there, and get to that location. So in that basic arterial with incident response location, we've got a MITS-enabled CARMA platform, CARMA Streets and CARMA Cloud. So the research questions are, can we reduce traffic safety conflicts, and can we measure that? Can we have the incident response vehicle traffic signal delay be reduced, right? So if we can get them there faster and safer, we will have achieved the goal. By doing this research, we feel we can develop some guidance for deployment and operations. And one of the things we'll do is we'll model a corridor, such as the Smart Drive test bed in Maricopa County, and we'll run some simulations. And then we want to be able to get out into the street and run some real live testing to show and demonstrate that we have developed a viable deployable technology. So if we go back and think of a little richer version of scenario one, this is the arterial incident, but now maybe we have some lane-by-lane controls. And lane-by-lane controls are not common things in traffic control today. There are some cases where we've done some things, changeable lane assignments in Houston and places, for example, where lanes are used either for left turn or for through, depending on the traffic movement. But if we could do the signalization where we could do a lane by lane, you can see this fire response vehicle on the left is getting through the signal, and we've stopped all of the other movements. And again, going to improving safety, keeping everybody but the one vehicle we want moving to move. It can also help with clearing the queue and getting those vehicles cleared and out of the way. The second vehicle is communicating with some of the vehicles that are in the roadway, using emergency vehicle alert and telling them to get out of the way. You can see down here on the right intersection, there's another fire response vehicle headed to the same incident, and so it's got the green arrow to allow it to go on its lane through the signal to where the incident is located. And then that would switch to clear the queue and get the other vehicles coming from the other direction. By having this view of multiple vehicles approaching, knowing the state of the signal and knowing what controls we have available, we can really make some intelligent decisions. So that's time one, and then after that vehicle goes through and then we switch, I call this time two. So we get to the other direction of movement of the vehicles. So again, you know, the research questions are essentially the same. Can we reduce the safety conflicts by using this traffic incident management with advanced TSMO type strategies? And can we improve the response time by reducing the traffic signal delay? And can we provide that guidance for deployment and operations? And can we demonstrate this both in simulation and maybe on a real test bed? And then the work zone presents another kind of interesting case. This is a case where we really do need the advanced information. We need to know that the work zone is on the route the vehicle is going to travel, and we might be able to do something like at the upstream signal, we might meter the vehicles that enter the work zone. And this is an example of a work zone that is at the Turner Fairway Highway Research Center. And so we could limit the vehicles getting in there, and then when the vehicles are also coming out of the work zone, we could give priority or preemption or priority at those signals to move the vehicles through. Okay, so this is another very interesting work zone. So can we use signal preemption at the upstream signal to mitigate congestion in the work zone when we know the vehicles are going to be responding, and can that help reduce the overall trip travel time? And again, developing guidance for deployment and operations and doing the modeling and simulation and some real-world testing if we can. So I've talked about a lot. I think it's an exciting opportunity. We would like to ask you to use the chat and give us some feedback about what do you think is the most important scenario? Have we left a scenario out that maybe we should be considering? And are there some major barriers to deployment and the kind of things that we're talking about? And so we'll give you a minute to add your thoughts there. I see that there have been some comments and questions put in the chat, and we'll get to those after we do this interaction exercise. I see a couple of people are typing, but I'm going to go ahead and move on to the next interaction question that we wanted to talk about. And, you know, our real intent in this project is to explore this CARMA ecosystem as a research platform for traffic incident management, and to see if we can't use cooperative driving automation to make an improvement in what occurs in traffic incident management. When I see pictures or hear reports of crashes involving incident response vehicles, especially at traffic signals, I know there's a lot of things that we should be able to do to improve it. And so this last question for you, again, use the chat please, is do you have any comments or suggestions about things that we could do to accelerate the research program, to accelerate the benefits that might be achievable? You know, our feeling is that if we can demonstrate benefits through our development, research development, demonstration and testing, then agencies will be more likely to be interested in adoption of this type of technology. I see Doug has posted a couple of comments that we'll respond to in the next section. Okay, so let's move on now to the question and answer session. Nicole, I'm going to hand it back to you to coordinate this part.
Great, sure. We have a couple questions. The first, I think Amir already addressed in the chat pod, but it would be great to bring this to the whole group. There was a question about the potential for CARMA simulation training. And so, Amir, if you wanted to elaborate on that a little more, that would be great.
Yeah, that's a great question. So under CARMA Support Services Program, as I mentioned, we're going to hold some training sessions, and the next one that we will be holding is a training session for SUMO software, which will be held sometime in summer, probably in July. But as of now, specifically to CARMA simulations, we haven't planned any training, but we might do that sometime in the future. So if we do that, we can actually advertise that through the CARMA, email.
Great, thanks, Amir. Our next question, are there any vehicle-to-vehicle or roadside or responder-to-vehicle commercial vendors participating in CARMA?
I can take this. Currently, majority of the commercial vendors that you have listed, Doug, are more so focused on the works on data exchange. However, through the CARMA program, we will integrate with the works on data exchange through CARMA Street, which is going to be like a V2I, which is how they will be able to participate. We are looking into these companies, but no formal relationship has been established yet. But definitely, we are moving forward in that direction.
Great, thank you. And I wanted to call back to a comment, Larry, on your prompt earlier about barriers to deployment. We had a comment that Colorado intermountain regions over 7,000 feet might pose communication challenges to connected vehicles.
Yeah, so that's an interesting question. I wonder if, I see in the comment that they're working with NIST and the wildland fire agencies to address that. And I don't know, if Federal Highway has been doing any kind of work on those kinds of issues related to wireless communication. It's not my area of expertise. Govind, or does anybody know if there's any work going on?
Hey, Larry.
Yes, sir.
Pardon me, I was putting my headset back on. This is Jim Ostrich. Just a quick comment. Not the problem exists whether it's for communications for automated vehicles, but in general, the responder community has this issue in states similar to Colorado, Wyoming, North Dakota, et cetera, where basically the bandwidth, if you will, communications capabilities for stretches of many, many miles, you know, are non-existent. So it's related to the, you know, the question at hand here, I think, and we do have a project regarding rural roads for traffic incident management, but nothing specific to, you know, connected automated vehicles.
It's a good topic to keep in the back of our mind as things are.
It is. Yep.
Great, thank you, Jim and Larry. Those were some really great questions. Thank you for submitting them. If there are no more questions, I don't see anybody typing anymore, so I think with that we can wrap it up. Thank you all for joining us today. If you have any more comments or questions or concerns, feel free to email carma@dot.gov, and we'll do our best to help you out.
All right. Well, thank you everyone for attending today's webinar. I also want to thank our panelists and moderator. We had some really good information today. Like I mentioned in the beginning, a recorded version of this webinar, along with the presentation, a recorded version of this webinar will be available on the NOCO website. On behalf of the National Operations Center of Excellence and our presenters, thank you for joining us today and have a great rest of your day.